Hello viewers. So we have this question under chemical kinetics. It says the gas phase decomposition of sulfuric chloride into sulfur dioxide and chlorine gas proceeds according to the reaction. So we are given the reaction and is first order in sulfuric chloride. At time t is equal to 0, pure sulfuric chloride is placed into a reaction vessel. The total pressure is measured to be 1.105 bar. As a function of time, the following data are obtained for the total pressure as a function of time. So we're given a table here that shows time in hours and also pressure in the units of bars. So at 0, when time was 0, we had a pressure of 1.107, and then when time is 3 hours, we have a pressure of 1.479. The question is calculate the rate constant for the reaction. So we're looking for the value of the rate constant. So let's go ahead and see how we can solve this. Now, to solve this, we need to start by having an ice table. We need to derive the formula that will help us find the rate constant in this case. So let's go ahead and do that. All right, so the chemical reaction we're given is we have sulfuric chloride, which is SO₂Cl₂, like that, and this is giving us on the other side we have sulfur dioxide, and this is being added to chlorine gas in that format. So the first step we're going to take is we're going to write our ice table, meaning we're talking about the initial, we're talking about the change, and we're talking about the final number of moles. So we're considering the change in the number of moles of the reactants and also the products. So initially, we only have number of moles that we are going to represent by N initial for only the reactant. And then on the product side, we don't have anything before the chemical reaction took place. After the chemical reaction has started taking place, we are going to have a change in the number of moles we have initially for all the reactants and products. So we are going to have change in the initial number of moles of this reactant here and also on the product side. Going on the change, what we are going to have is this initial number of moles is going to reduce since we have something here and we don't have anything on the other side. In other words, reactants are going to reduce and products are going to increase. So we are going to say this is going reducing by the degree of dissociation multiplying by the initial number of moles. And what we lose there is what we are gaining here. So we have the degree of dissociation multiplied by number of moles, and we're having the same on the other side like that. At equilibrium, what we're going to have is the initial number of moles subtracted by the degree of dissociation, that is multiplying by the number of moles initially, and here we're going to have just the degree of dissociation multiplied by number of moles initially, and we are going to have the same on the other side like that. So this is our ice table, and this is what we are going to have at equilibrium or at the final stage here, as we can see. So when we reach this stage, what we need is to find the total number of moles at the final stage. So we'll say N total, let's represent it as NT, is equal to the sum of the number of moles for each reagent involved in this chemical reaction. So we have this added to that, then added to that. So let's do that. So this will be N initial minus alpha N initial. This whole thing here must be added to alpha N initial. That is being added to alpha N initial like that. This will be equal to, we'll have our N initial minus alpha N initial here like that. This will be added to, now when we add these two are the same. So when you add this to that, what you're going to get is just 2 alpha N initial. So that's what we are going to have here, 2 alpha N initial. So this will be equal to, we'll have our N initial minus alpha n initial that is being added to 2 alpha n initial. Now, when you look at these two here, these are like terms. So we'll say we have minus alpha n initial added to 2 alpha n initial. And this will give us, taking this on the other side, what we're having is we're going to have n initial. Then this is just added to alpha n initial. So this is what we are going to have as our total number of moles. In other words, we have Nt is equal to n initial that is being added to alpha n initial, like that. And when we look at what we have here, we can say we have something that is common. We have n initial here, and we also have n initial on the other side. So we're going to factor out the n initial. When we do that, what we're going to have is our n total is equal to n initial factored out. Then we'll have 1 there added to, on the other side, we are going to remain with alpha. So it implies to say this is what we have as our total number of moles at the final stage. Yes. After finding the total number of moles, our next step is to find the degree of dissociation. We want to find what we can replace on the degree of dissociation here. So let's go ahead and find that. So to find the expression that will represent the degree of dissociation, we're going to use or apply the decay formula. That says the number of moles at a time for a certain component is equal to the initial number of moles of that component multiplied by E to minus KT, where the K we have here is the rate constant, T is time, N naught is initial number of moles, and Nt is the number of moles at a time for a certain component. In this case, we are talking about sulfuric chloride. So the number of moles of sulfuric chloride at the final stage is equal to the initial number of moles multiplied by E to minus Kt. Now, when you go back here, on our table here, you can see it say at the final stage, the number of moles for sulfuric chloride, in this case we are considering sulfuric chloride, the number of moles of sulfuric chloride at the final stage is N initial minus alpha N initial. So this is what we are going to replace on the other side. So we'll say what we have is, on this part here, what we are going to have is now, we have N initial minus alpha N initial, and this is equal to N initial given to E to minus KT, like that. On the left-hand side here, we can factor it out to make our mathematics easier. We'll say we have N initial here and N initial there, so we have something that is common. We'll say we have N initial outside, and then we'll have 1 minus alpha, which is the degree of dissociation, and this is equal to N initial, then E to minus KT, like that. When you read this stage, all we have to do is we're going to divide by N initial, and then we'll divide by N initial here. What we're going to get is 1 minus the degree of dissociation is equal to E minus KT, like that. Making the degree of dissociation the subject, meaning making this the subject, we are going to take it on the right-hand side and take this one on the left-hand side. When we do that, what we'll have is we'll have our degree of dissociation to be equal to 1 minus E to minus KT. So this is the expression that will replace the degree of dissociation in our calculations. Now that we have that, all we have to do is go back and replace in our expression for the total number of moles here. So we have the total number of moles here to be equal to the initial moles multiplied by 1 added to the degree of dissociation. So we're going to replace what we just found on the degree of dissociation. So let's quickly do that. So what we have is, we have our NT to be equal to N initial, then we have 1 added to the degree of dissociation, like that. Replacing, we'll say this is equal to n initial, and this will be 1 added to 1, we're replacing now, minus e, that is given to the power of minus kt, like that. When we do our mathematics here, we'll see that we have n initial, 1 plus 1 is 2, so this will be 2 minus e to the power of minus kt, like that. So this becomes our total number of moles now, after replacing our alpha in that case. Yes. All right, so after finding the total number of moles, the next step we're going to take is we need to recall that. So we'll say recall that the total pressure using the ideal gas law equation is equal to the total number of moles multiplied by RT, that is being divided by volume. And also, if we are looking at the initial pressure will be equal to the number of moles initially multiplied by RT also divided by volume, like that. So we need to recall these two equations here for pressure. After doing that, we're going to divide the two. We're going to say the total pressure divided by the initial pressure. So that's what we are going to do. So we'll say we have PT, we said PT is equal to NT multiplied by RT over V, where PT means the total pressure and NT means the total number of moles. R is a constant, T is temperature, and V is volume. For the initial pressure, we'll say this is equal to N naught, where N naught is the initial number of moles. This is multiplying by RT as well, and this is dividing by V. So we are dividing the two equations. We are dividing this equation by that equation there. So let's do that. What we are going to have here is we'll have PT divided by P initial. What is on the left side, divide, and what is on the right side will also divide. So we'll have NT RT like that, divided by V. And this whole thing here is being divided by N initial RT, which is divided by V, like that. So what we're going to have is we'll still have our PT divided by P initial. On the other side, we'll say we have our NT RT over V. Now, this is like divided by N initial RT over V, like that. Taking it on the other side, what we have is PT over P initial. This is equal to, we'll still have our NT RT, like that, over V. And this now will multiply by, we are going to switch those two. Our volume goes on top, and our N initial RT becomes down. So when you do this, you find that our RT and RT will cancel, our V and our V will cancel. So RTV are cancelling. So what will remain now is PT over P initial is equal to NT divided by N initial, like that. So PT over P initial, this is equal to, we're now going to replace where we have the total number of moles with the total number of moles we found earlier on. So we're going to replace by this here. This, we said our N total is equal to N initial 2 minus E to minus KT. So this is what we're going to replace on what we have there. So let's do that. So we'll say on this stage now, we're going to replace our NT by N initial. Then we have 2 minus E to minus KT, like that. And then down here, we still have our N initial. So this will give us our PT over P initial to be equal to, on the other side, those two will cancel. This and that will go, and what will remain is just 2 minus E, that is given to minus KT. So that's what we are going to have at that stage. Yes. So when you reach this stage, remember we are looking for K. We are looking for K. So we're going to make K the subject of the formula. From this expression that we have here, we'll make K the subject of the formula. So let's do that. From what we are given here, what we have is PT over P initial is equal to 2 minus E to the power of KT. So the first step we're going to take is we're going to take this 2 on the other side. So when you do that, what we are having now is going to be PT over P initial. When the 2 goes on the other side, it will be minus 2. And this whole thing will be equal to minus E, not E, but minus E. We'll have minus E to the power of minus KT like that. Yes, that's what we are going to have. Now, we don't want our E to have a minus here. We want our E to be positive. So in order to get it to be positive, we're going to multiply by a negative, this side and that side. When we do that, what we're going to get is, we'll have minus PT. Let me rewrite that. So we'll have minus PT over P initial added to 2 to be equal to E to the power of minus KT. So that's what we are going to have there. So when we reach this stage now, we are going to introduce natural log. Remember, natural log is the inverse of the exponential here that we have E. So when you introduce natural log, we are going to get rid of this E. We want to get rid of this E so that the minus KT can come down, since we want to make K the subject of the formula. So we're going to introduce natural log here and also on the other side. So that's what we are doing next. So what we are going to have is, I'll start by writing natural log of E to minus KT. This is equal to natural log of everything there, which is minus PT over P initial, that is being added to 2, like that. So that's what we are going to have there. Proceeding, the natural log and E are going to cancel. So this and that will cancel. What you have now is minus KT has dropped down, and this will be equal to still the natural log of minus PT on top there, then minus P initial down there, then this is still being added to 2. So that's what we are going to have in that case. Still like that, we're talking about the whole expression. So when you reach this stage now, the best we can do is now replace with the values we have. We have the PT, we have P initial, we have T, and what we are looking for is K. So we'll say now this is going to be minus K, that is being multiplied by 3. Remember the time we are given is 3 hours. From 0 to 3 hours, that's 3 hours covered. And then this is equal to natural log of, now we'll have minus, on top there, our pressure at a time is given to be 1.479. And this will divide by, down there we have 1.107, like that. And this whole thing here must be added to 2. So this is what we have here. And this is going to give us, on the left side, we still have K multiplying by 3. And this is equal to the natural log of, now what we have inside there when we do mathematics is we are getting a 0.663 0.96. So this is what we are getting there, rounded off to 1, 2, 3, 4, 5 decimal places. So this is going to give us minus 3k, let's put it in that format, to be equal to the natural log of 0.66396 is giving me a minus 0.4095. So that's what I'm getting. And since we have negative negative here, we don't want our k to be a negative. So we're going to multiply by a negative. So when we do that, when we multiply by a negative, what we're going to have is we have 3k to be equal to 0.40954. And now we're going to divide by 3, and we're dividing by 3 on the other side. This will give us a value of k to be equal to, according to my calculator here, it's giving me a 0.137. And the unit is per hour. This is rounded off to 3 decimal places. So this is our answer for the value of k. And this is how we solve this question. So if you found this to be helpful, support us by subscribing to our YouTube channel, like, comment, and share